Imagine building an entire world out of billions of tiny Lego pieces. You stack them together, trying to create something meaningful, a phone, a desk, or even a living body. But there's a problem. None of them can stick together. They slide apart, drifting into a pile of loose blocks. Now imagine the same thing happening to the real world. Your phone dissolves, your desk vanishes, bodies begin to break down. Not because something exploded, but because the tiny forces that hold atoms together suddenly disappeared. These invisible forces are called chemical bonds, and are the reason matter can exist in organized structures. Without them, atoms would behave just like those loose Lego pieces, unable to build anything at all. But what makes atoms stick together in the first place? For understanding that, we have to travel to the very edge of the atom, a region chemists call the valence shell. Each atom has another electron layer called the valence shell, and atoms are the most stable when this shell is full. But many atoms start out incomplete. Atoms with incomplete valence shells tend to interact with other atoms so both can fill that outer shell. They do this in two main ways. They either share electrons or transfer them. These interactions usually result in atoms staying close together, held by attractions called chemical bonds. Some of these bonds are especially strong. The two strongest types are covalent bonds and ionic bonds. However, about ionic bonds, when their compounds dissolve in water, the interactions become much weaker. A detail we will explore later. Now let's start with covalent bonds. A covalent bond happens when two atoms share a pair of electrons. Take the simplest example, imagine two hydrogen atoms. Each hydrogen atom has one electron, but its shell can hold two. When two hydrogen atoms come close, their electron clouds overlap. Instead of fighting over the electrons, they share a pair of electrons. Now each hydrogen atom effectively has two electrons in its shell, in the way that both atoms are satisfied. Whenever atoms are held together by covalent bonds, the result is called a molecule. But if atoms want electrons this badly, why would they share them in a covalent bond, instead of one atom simply taking them from the other one? The answer lies in the property that determines how strongly an atom pulls on electrons. It's called electronegativity. The more electronegative an atom is, the more strongly it pulls the shared electrons toward itself. Think of a covalent bond as a tug-of-war over electrons. If both atoms pull equally, the rope stays in the middle, such as covalent bond between two hydrogen atoms. This is called a nonpolar covalent bond. But sometimes one atom pulls harder. When electrons are shared unequally, the bond becomes polar. A perfect example is water. In a water molecule, oxygen is more electronegative than hydrogen, so the shared electrons spend more time near the oxygen nucleus than the hydrogen. This gives the oxygen a partial negative charge and a partial positive charge to the hydrogen. That tiny imbalance gives water many of its remarkable properties, including the reason ice floats on water. Not all the bonds are this polar though. In methane, carbon and hydrogen have similar electronegativities, so the bonds are much less polar. In some cases, two atoms are so unequal interactions for valence electrons that the more electronegative atom strips an electron completely away from its partner. And the result? Well, the two particles with opposite charges are now called ions. Let's look at a familiar example, sodium chloride. Sodium and chlorine don't attract electrons equally. In fact, chlorine has a significantly higher electronegativity, meaning it pulls on electrons far more strongly than sodium does. When these atoms interact, this difference becomes decisive. The single valence electron from sodium is pulled strongly toward chlorine. Eventually, the electron is no longer shared between them. It is effectively transferred. As a result, sodium loses that electron and becomes a positively charged ion. Chlorine gains the electron and becomes a negatively charged ion. Now, because opposite charges attract, the two ions are pulled tightly together, forming an ionic bond. Covalent and ionic bonds are the strongest ways atoms hold together. They build molecules, crystals, and much of solid structure of matter. But in living systems, something surprising happens. Some of the most important interactions in biology are actually much weaker. Individually, they're fragile, almost insignificant. Yet together, they shape the behavior of water, the folding of proteins, and even the structure of DNA. So, how can forces this weak hold life together? That's what we'll explore in the next video, where we'll uncover the surprisingly powerful role of weak chemical interactions. If you enjoyed this video, make sure to watch the next one.